All right. Hello, I'm Rob Clark from the Chrome OS GPU team, and here to talk about something a little bit different this time. This is kind of a little bit more of a idea I have had and something I've been thinking about more than a finished product. All right, can you hear me? So, anyways, I made the mistake of starting to think about webgl and more so webgpu in the context of security, and I mean, let's face it, GL and Vulkan drivers are not really designed as a hardened security barrier. They're designed to have more FPS. So on the Chrome side, one of their security principles is the rule of two, which is pick more than no two of these three things. So, something processes untrusted input, it's implemented in an unsafe language, and it has high privilege, i.e. it's not sandboxed. And I kind of think that the Vulkan or GL driver doesn't quite follow that. So that's what this is about. So, but first some terminology, just so we're all on the same page. When I say KMD, I mean the kernel mode driver, so the DRM driver. When I say UMD, I mean user mode driver, i.e. mesa. And then another concept I'll mention is origin, and that means basically what the web server is. It's a combination of protocol, host name, and port. In the web context, there's this same origin concept. So scripts like JavaScript and such are limited in how they can interact with content from another origin. So basically, stuff that's coming from the same web server trusts each other. Stuff that's coming from a different web server doesn't trust each other, i.e. you don't want some like typo squat URL to pull up a full screen iframe with your actual web email and be able to like scrape the contents of that. So yeah, like I said, this is basically about what happens when you consider hostile content versus webgl and webgpu. And Vulkan specifically calls out undefined behavior. It specifically defines valid usages and says anything that's not a valid usage is undefined. GL doesn't really specifically call this out, but you can still crash a GL driver. So both WebGL and WebGPU layer atop of the user mode driver does implement some basic protections, bounds checking. They attempt to do some shader validation, things like that. But, Vulkan and GL are very big API surfaces. They both contain a shader compiler, for example. I think that trying to protect every possible attack from above is just not feasible. I mean, you can still crash a user mode driver if you try, or sometimes even if you don't try. So my thinking was, okay, well, what if we flip this around? Instead of trying to protect everything from above the driver and playing, an endless game of whack-a-mole, what if we just considered the user mode driver as a crumple zone? Just plan on bad guy getting code execution there and try and make things so that didn't matter. So, not necessarily removing the basic sanity checking that WebGPU and WebGL have, but just plan on that not being sufficient. So how would that look? That would look like having a separate sandbox process for the user mode driver for every unique origin using WebGL or WebGPU, which conveniently fits better with the kernel's view of process isolation. I mean, so it'll guarantee that you get a separate GPU virtual address space for each origin. Things like information mitigation leaks applied by the kernel happen on essentially process boundaries. So you want to have that happen when you're going between webgpu or webgl content from different origins. And this fits with the web same origin policy, like I was saying earlier. The same origin policy limits interaction from script content to resources from other origins. But okay, you've done all that, but your user mode driver still needs access to the kernel mode driver. And it turns out there can be bugs there too. This is just a non-representative sample of KASAN and vulnerability reward program bugs that were assigned to me in, say, the last 3 or 4 months. That's not including ones that I reassigned to someone from AMD or Intel. It's just the ones that I handled myself. And even worse, when there are kernel bugs, there's a lot of kernel versions out there. Different distributions are on different kernel versions. Some, more enterprise or slow-moving distributions might be on older kernel versions. Chrome OS until recently had Intel Chromebooks on, I think, 5 different kernel versions back to 4.14. I mean, more recently, that's the oldest we're on right now for Intel is 5.4, but still, I've had bugs that I've had to backport to 5 different kernel versions and then cherry picked beta and stable and Chrome OS long-term branch, so that quickly becomes a lot of places to get fixes for kernel bugs rolled out to. And the reason for this is, okay, if we're just assuming someone's going to get code execution in the user mode driver, we don't want to turn that into a jumping off point to, a vulnerability in the kernel. So can we isolate the user mode driver from the kernel mode driver? Well, we actually kind of already do this in the case of VM guests and virtgpu native context. In this scenario, we have the native user mode driver in the guest. We don't trust the guests. The user mode driver can crash. Okay, that's fine. We have the native kernel mode driver in the host. The interface is serialized over virtq. So what if we did that in a different context? What if we serialized over a socket instead? And this is actually something that Virtual Render already has called vtest, which is at least useful for a prototype. And it's also conveniently useful for debugging and testing of native contexts. So it's kind of a useful thing to have regardless. So this has some nice properties. I mean, we're already considering it a security barrier in the VM use case. In the host side or the side that has access to the kernel mode driver, it's actually single-threaded, doing non-blocking calls to the user mode or to kernel mode driver. And actually this alone blocks like probably 80% of the bugs that I've seen. I mean, most of them are require race conditions to trigger. It also helps ensure ioctls are well formed. I mean, we know that when you have pointers in the ioctl payload, they're going to be to valid memory. You're not going to see weird things like pointers to unfaulted gem objects or anything like that. And at the bottom is a link to an MR I have up that's adding a VDRM helper in Mesa, which basically will, so native context implementations that use this will work automatically also with vtest. And by the way, I mean, as I've been seeing these bugs come in, I've kind of been conducting a mental experiment of, could this bug in the kernel have been reached through native context? And so far for the ones I've seen, the answer has been no. I mean, probably doesn't block everything, but blocking nearly everything is a significant improvement in your defense and depth posture. So on the topic of performance, the one drawback compared to native context in a VM is it does make your command submission synchronous, i.e. you don't have guest fences like you do in the VM guest, so you have to wait for a reply on the socket to get your fence FD or sync object IDs passed back. But its round trip latency is less than a guest. So in pedantic cases, like if you look at something like GL Mark II build, which is just a bunch of submits with a single draw each, then it can be like 10-15%. That's like, you know, something that's running at 5,000 FPS or so. For more realistic workloads, it's not so bad. And when you're thinking in particular about hostile environments, I think maybe it's worth the trade-off. So other potential alternatives, we could, on the kernel side, implement a one-way switch per DRM file to add locking to serialize all of the ioctls against that DRM file. I mean, the idea is it'd be a one-way switch that you flip before the sandbox starts handling untrusted GL or Vulkan content. The main awkward thing about that is blocking ioctls. I mean, serializing all your ioctls when you have like a wait fence ioctl is not great. You know, drivers using native context are already kind of planning around this and do all of their waiting by polling on a like DMA fence FD or similar. The other thing, which actually would be really nice, you know, to have eventually, is more Rust in the kernel. I think Rust could at least, if done right, protect against a lot of these issues. You know, I think it will take some time to get there, especially when you consider the age of a lot of the kernels out there. So I think that's probably the right long-term solution. In particular, having the parts of the driver that handle the render node U API. But I think, you know, it's maybe not a short-term solution. So anyways, that's what I have. Questions?
Wouldn't the same origin kind of policy be like hard coding that would be problematic for sites that are hosting for content like shadertoy.com or cables.gl?
I didn't. I mean, the point in bringing that up is that there should be that the browser imposes isolation between and limits the amount of trust on scripts from one origin to another, and you know, by analogy, we should have separation of, you know, like if one origin manages to corrupt GPU memory, for example, or trigger something that reads GPU memory, it shouldn't be able to read another origin's GPU memory. Does that make sense?
Yeah, I guess you mean that you could have, like that's one example of a policy that could be applied.
Yeah, well, I mean, it's something that we're kind of not following by having, say, a single GPU sandbox, or not having a sandbox at all. All right, did I put everyone to sleep? All right, well, thanks.